Hello and welcome to this video on representing inequalities using the real number line and interval notation. Alright, so I just have several examples here. We're going to be working with inequalities and a closely related topic to inequalities is intervals. And going back and forth between inequality notation, interval notation, and then the graph of an inequality, a picture of the solutions of an inequality. So let me begin with this example here. So I have, for my first several examples, I'm going to be doing the following. I'm given an inequality, and this one is a compound inequality. If you're not familiar with compound inequalities, please review those. Either look for other videos on them or go into your text and whatever material, Google it, find material on compound inequalities. But here I have inequality notation, and I'm asked to graph the inequality. Remember, whenever you're asked to graph something in any respect, when they say graph, that just means draw a picture that represents solutions. Draw a picture of the solutions, alright, whether it be to an equation or an inequality. Okay. Then we're going to write the inequality in what's called interval notation. Alright, so I'll get to that at the very end of this page. Alright, so the first inequality I'm looking at is actually what they call a compound inequality, right? It's multiple inequalities. You have the two inequality symbols here. Multiple inequalities considered in the same statement. You have -3 is less than or equal to x, and x is less than or equal to 2. So what I said there is the equivalent form of this. This is the same thing as saying -3 is less than or equal to x, and, right, word and there, x is less than or equal to 2. Okay. So in order for a number to be a solution, in order for a value of x to be a solution to this inequality, it must satisfy both of these inequalities at the same time. Alright. In other words, x needs to be a value between -3 and 2, or equal to -3 or 2. Right. So first I'll talk about the graph of the inequality. Now there's a single variable here, usually that indicates that we're going to be working on a single number line. Alright, so here's a representation of the real numbers, the real number line. Again, if you're not familiar with this, every single point on this line I've just drawn will represent a number, where, say, this point right here represents the number 0, and then you have positives to the right, negatives to the left, and it goes +1, +2, etc. And then even the points in between represent things, like you could represent a half, you could represent the square root of 2. All the real numbers are represented by some point on this line. And then going this way, you count backwards, -1, -2, etc. And again, you can represent any number with a point on this line, -1,000,000 and whatever. And whatever you want, whatever real number you want is represented by a point on this line. And if one number is to the left of another number, then the number on the left is considered smaller. So for instance, -2 is to the left of 1. So they would say that -2 is less than 1 or smaller than 1, and 1 is greater than -2. Even though 2 and 1, 2 is bigger than 1, but -2 is going to be considered smaller than +1 because it is to the left. It is on the lower side of the number line. Okay, so the graph of this particular inequality, again, it's a picture of all the solutions to the inequality. Numbers that I can replace x with and make this a true statement. Well, numbers like this I mentioned earlier are numbers between -3 and 2. Alright, so I'll mark off. Keep going here. There's -3. There's +2. So every number in between, -2 is both greater than -3 and less than 2. -1, 0, 1, -1.5, negative square root of 2, negative square root of 3, and positive square root of 2, 3/4, whatever. All of these numbers between -3 and 2 are solutions. Now you can put individual little dots, but I'm going to make that every single number in here is a solution. Right? So I'll indicate that above here by marking off a little segment every number in between. Okay. Now what about the endpoints? You have there's -3 is at the left endpoint of this graph, and +2 looks like it's at the right endpoint. What about those endpoints? Well, how about, alright, so -3 itself, let's just check it out. Replace x with -3. Is -3 less than or equal to -3? Well, yes, it satisfies the or equal to part. And at the same time, is -3 less than or equal to 2? Well, yes, it satisfies the less than part, right? These less than or equal to, greater than or equal to symbols, as long as one of them is satisfied, it's true. So -3 is less than 2, that's true. -3 is equal to -3, that's true. So, yes, -3 is a solution. Now, to indicate this, I guess it depends on what textbooks you're looking at. Some books, to indicate that endpoint is a solution, will just close it off, close the left endpoint off with a nice closed dot. So a nice solid dot here, right, could indicate that the endpoint, that number at the endpoint, is a solution to the inequality. Right. Same thing for 2. All right, look at the right endpoint, the number 2. Let's test that out. So I'm going to go and replace x with 2. Is -3 less than or equal to 2? Yes, it's less than 2, right? So this is satisfied. And at the same time, is 2 less than or equal to 2, right? Again, replacing x with 2 in here, right? And yes, 2 is equal to 2, right? It satisfies the equal to part. So both are satisfied. So the number 2, the right endpoint, is also a solution. All right, so I'll indicate that with a solid dot above 2. And there's a graph. All right, there's a good solid graph of this inequality. Now in some texts you may see this, right? So I've got the solid dots at the end. You might see, say here's my real number line. Here's 0, and then let's say, again, 2's to the right of 0. Let's say that's where 2 is, and then -3 is to the left of 0. Let's say that's where -3 is. And all the solutions, as we mentioned, were all the numbers in between -3 and 2, right? All of these numbers satisfy these inequality, this compound inequality. And then in some texts, you might see that, to say that one of the endpoints is a solution, you might either put a solid dot, like I mentioned here, right, the solid dot, or you might put a rectangular bracket that opens in the direction of the solutions. So on the left endpoint, I'd put a rectangular bracket that's opening to the right. And on the right endpoint, 2 is a solution. You'll see a rectangular bracket, little with the 90-degree angles here above 2 that's opening to the left. Okay, so these rectangular brackets, right, with the little 90-degree crooks, those also indicate, again, depending on what book you're looking in, those will also indicate that the number at the endpoint is a solution to the equation or inequality I'm looking at. Right. So this is also valid. So either of these graphs is fine. All right. I personally prefer just doing a solid point. Okay, it's a little less writing, I guess, and also too, I have found that when you teach it with the brackets, people tend to rush them. You know, they draw them too quickly and make them too rounded, and then it gives it a totally different meaning, as you'll see in the next example. Okay, all right. But for right now, here's the graph of this inequality. This a picture of all the solutions. And now I'm going to do what's called I'm going to write this inequality in what's called interval notation. So I'll be on the next page here. Now, interval notation, this is just a way to represent an interval of numbers, a range of numbers on a number line. All right. And when you're writing an interval, I'll make this note right now. When writing an interval of numbers, always write them from lowest to highest number. Right? And if I'm talking about the number line, that'll be from left to right. But later on in your math studies, you'll also see writing intervals on a vertical line. This is a horizontal line, horizontal axis. There might be two axes later, a vertical one and maybe even a third one later coming out of the page, a z-axis, x, y, z. So I'm not going to necessarily say from left to right, because you might also be going from bottom to top. So I'm just going to say always write from low number to high number, from low to high. And in this case, in this example, this will be from left to right. All right. So what do I mean by this? All right. So what we're going to be doing is, first I'm going to look at my picture. All right. Now you can also look at the actual inequality. All right, I'll pull that up. Again, I prefer this graph with the solid dots. You can use the graph with the brackets if you want. So I look at my inequality, or I look at my graph, a picture of all the solutions, and I notice there's this one interval, this one range of numbers that make this a true statement. So the interval for this, as I look at this from low to high, right, from low numbers to high numbers, so left to right on this horizontal number line, the first number I'm going to write is the left endpoint, where I enter this interval. So I'm going to write -3. Okay, so you have your left endpoint written down first. All right, then a comma. All right, then a comma, and then again going from left to right. I've got -3 as the left endpoint, and then all of the numbers after -3 to the right of -3 are solutions, and then where the interval, where this piece of numbers, where this interval of numbers ends, is this right endpoint of 2. So you put the left endpoint, comma, and then the right endpoint number of the solutions. Right, the right endpoint where we would exit the solution set. And then you're going to cap these off. All right, you write my left endpoint, comma, right endpoint, and then we're going to cap them off with either a square bracket or a parentheses or a parenthesis. So kind of like the graph I put up earlier. You're going to put either one of these square brackets, these rectangular brackets, to indicate that the endpoint is a solution of the inequality. Or you're going to put just a straight up parenthesis, right? Either opening to the right or opening to the left, depending on which endpoint you put it on. If you put up a parenthesis, that will indicate that the endpoint number, right, the number at that end, is not a solution of the inequality. Alright, so let's keep this in mind for our, all the examples after this. Okay. So as we saw in my graph earlier, we checked these endpoints. -3 is a solution of the inequality. So that means I'm going to put a square bracket, and since it's on the left endpoint, I'm going to have it facing to the right. Okay, actually open around the number. I put this square bracket on the -3, again indicates that -3, the left endpoint, is a solution of the inequality. Makes it true. And we also noted that 2, right, the right endpoint, is a solution. So again, a square bracket, and since it's on the right, I'm going to have that bracket opening left. And then here, right, this right here is our interval, what they call the interval notation for this inequality. It's a way to indicate what numbers are solutions. This represents, -3 is a solution, 2 is a solution, and it implies that every number in between, the interval of numbers in between these two, are also solutions. Okay. All right, and one other thing to point out, another definition, another word you're going to see, is if you see a interval like this, where both ends and where a and b are real numbers, like -3 and 2, and both ends are these rectangular brackets, like I have here, this kind of interval is called a closed interval. Alright, it's a closed interval, like meaning the two ends are capped off, and they belong. The two endpoints belong to the solution set and cap it off. It's completely closed. You can't like exit it. Right? That's not a real straightforward. That's not a real valid definition there. But it's good enough for now. Okay, so that's the first example, and I've got plenty of others. Go through them a little more quickly. The next one I have is another compound inequality where I'm asked to do the same thing. I'm saying graph the inequality, and then write the inequality in interval notation. Alright, so here I have 3 is less than or equal to x, and, right, because they're connected, this is an and compound inequality, x is less than 6. Right, so again, I'll write this in its equivalent form over here. This is the same thing as 3 is less than or equal to x, and at the same time x is less than 6. Right. Okay, so first I'll do the graph. All right. So here's the real number line. Just say that's where 0 is, and the numbers being mentioned here are 3 and 6, so I'll mark those off. Now 3 would be to the right of 0. Let's say there's 3, and 6 is larger. It would be to the right of that even further, right? Even further to the right. So here's 3 and 6, and think of all the numbers that are solutions to this. Think of all the numbers that make this a true statement. Like 4, 5, and 4.5, 5.5, 5.9, right? Any number that's both greater than 3 and at the same time less than 6. So every number between 3 and 6 is a solution. So I'm going to indicate that here. Right? Every number between them is a solution. Numbers over here like 7 or 8 aren't less than 6, and numbers over here like 2 or 1 aren't greater than 3. So only these numbers between 3 and 6. Now how about the endpoints? Right. 3 is at the left endpoint. Does 3 satisfy both? Well, 3 is less than or equal to 3 because of the equal part. That's true. And 3 is less than 6. They're both true. So the whole thing's true when x is 3. So as with the last example, I can put a closed point above that left endpoint. 3 is a solution. Or you could put that rectangular bracket that opens to the right to indicate that 3 is a solution. Alright, but how about 6? Alright. Now is 3 less than or equal to 6? The right endpoint? Yeah, that's true. 3 is less than 6. That works. But at the same time, is 6 less than 6? Well, no. 6 is not less than 6. 6 is equal to 6. So this is not true. Alright, this is not a true statement when x is 6. So to indicate that, again, we can do this a couple ways. One is, instead of with a closed filled in dot, I can indicate that by putting an open dot, an open point over that right endpoint of 6. So off to the side here. So an open point, just an open dot, will indicate that the endpoint is not a solution of the inequality or whatever we're looking at. Alright, and just like I mentioned in interval notation, if you put parenthesis, right, just a parenthesis or parentheses, that'll indicate also that an endpoint is not a solution. So you might also see the graph of this look like this. Here's the real number line again. Say there's 0 and 3's to the right of that, 6 would be further to the right of that. All the numbers between 3 and 6 are solutions. 3 is a solution, so put a rectangular bracket on that, and again that would have to open to the right to be opening toward the solution set. And 6 is not a solution, so I put a parenthesis. See again, I honestly just prefer the open dot, closed dot form, because you can see it again. If you rush drawing your brackets, you might accidentally put like something that looks too close to being a parentheses, and that means something totally different. If you accidentally write a parenthesis, if you rush it, it'll mean that number isn't a solution when it actually is. But so rectangular bracket on the left endpoint, parentheses on the right endpoint, those two graphs mean the same thing. Alright, and now for the interval. Alright, writing the same solution, writing the same set of solutions in interval notation. Again, I just go from low to high numbers, right? Go from left to right always. And when I first enter the solution set here, the left endpoint is the number 3. So I put the number 3, my left endpoint, comma, and then there are solutions to the right of 3, solutions, 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 and then I exit this piece. I leave the solution set at the right endpoint here of 6. So this is implying that every number between 3 and 6 is a solution. This 3 comma 6. But then you have to also put the little caps on to say whether or not the left endpoint or right endpoint are solutions. So the left endpoint we saw was a solution, so the rectangular bracket, again, be careful drawing these, make sure it's nice 90-degree angles. You put a right, don't make it like a parenthesis. Put a little rectangular bracket there to indicate that 3 is indeed a solution. And 6 we determined was not a solution to this inequality. Did not make it true. So again, be careful, make it curly parentheses around that. That indicates that 6 is not a solution. Alright, so there's your graph of the inequality solutions. Here's an interval describing the inequality solutions. Again, all this means is that every number between 3 and 6, including 3, but not including 6, are solutions to this inequality, which we see in our picture as well. All 3 of these things mean the same numbers right? The inequality notation, the graph notation, the interval notation all represent the same number set, right? And then off to the side here, if you have an interval where one side is a parenthesis, or one side's a parenthesis, one endpoint has a bracket on it, or maybe the left end has a parenthesis and the right end has a bracket, and then a and b are real numbers like 3 and 6. This kind of interval is called a half closed, right? Half of it is closed, half of it has the bracket on it, or half open. We'll see an open interval, fully open interval in a second. But the openness will be from the parentheses, the half of its parentheses. So it's called half closed or half open. And in some books you might even see this called clopen. It's kind of funny. It's just a mixture of closed and open. But yeah, just most texts though that you're going to see in intermediate algebra, beginning algebra, we'll call these things half closed or half open. Right, so what I have here is a half closed or half open interval. Great. So here's yet another inequality where I'm asked to do the same thing. Graph the inequality and then write the solutions in interval notation. So this is not a compound inequality anymore, right? There's only the one inequality symbol, the is less than or equal to symbol here. So I have x is less than or equal to 3. So we're again trying to think of solutions to this. Right, so first I'll draw a graph on one variable, so just one number line representing possible values of that variable. Right, maybe even sometimes you might label it like these are possible values of x. And I didn't do it for the first couple of examples. I usually don't, but and then here's where 0 is, and now the only number mentioned here is the number 3, which would be to the right of 0, and it's greater than 0. Alright, and then I'll indicate above this where all the solutions are, right? Where all the numbers I can replace x with to make this a true statement. Well, 2 is basically anything less than 3, right? 2 is less than 3, 1 is less than 3, negative 5.5, negative pi, all the things left of 3, right? 2, 0, all these numbers here, right? And then I'll indicate that by just drawing a nice ray. But, the thing is though, in my previous two examples, there was a left end point. There was a point where it stopped. This one does not have that luxury. Negative 1, negative 2, negative 3, negative a million, negative a billion, negative a trillion, negative Google. All those numbers are less than 3. And so this is going this way. All these numbers are solutions forever. And I can't possibly draw that. Or I can't draw something forever. So I'll indicate that with a little arrow here to indicate that there is no left end point. It goes on this way forever. There is a right end point, however. Right? It doesn't go beyond 3. And let's determine if that right end point is actually a solution or not. So if I plug in 3, is 3 less than or equal to 3? Well, yeah, it's equal to 3. It satisfies the equal part. So 3 is a solution. And again, I indicate that an endpoint is a solution with either the closed point like this, or I could have put a rectangular bracket that opens to the left. All right, I'm going to stick with the closed point thing here. All right. Now for the interval notation. Again, we're going from when you write out your intervals, you always go low numbers to high numbers. Now looking at my picture, right, looking at all the solutions here, there is no left endpoint, right? There is no lowest solution. So to indicate that there is no left endpoint, you could say that the solution's left endpoint is negative infinity. Right, it goes on this way to the left forever. I'll put it off to the side here. When you write negative infinity, this is not a number. right? I'm going to make that note. People tend to, in infinity, right, the infinity symbol there is not a real number. It's an idea, it's a concept, all right? This would just indicate that there is no left endpoint. There is no smallest solution. There's all, you say, oh, negative a million is the smallest. Well, what about negative a billion? There's always one smaller. So there is no left endpoint when you put negative infinity in your intervals. All right. So instead of a left endpoint for my interval, I'm going to put the negative infinity. All right, comma. So that means there is no left endpoint. Goes to the left forever, all my solutions, comma. And then is there a right endpoint? Yes, there is, right? As I move from low to high numbers here, I go through all these solutions, from negative infinity all the way to the left forever, all the way up till 3, right? 3 is where I exit the solution set. So there is a right endpoint of 3. So this tells me that all the solutions, to the left forever, all the numbers below 3 up to 3 are solutions. All right. And now for the caps, right? Do I put a bracket or parentheses? Well, I mentioned to you already up here that infinity, right? And same thing with negative infinity. Infinity, negative infinity, those are not real numbers. So you always put a parenthesis, either this one or this one, on negative infinity or infinity, right? Because they don't, you can't plug those in. If I said to you, is negative infinity a solution to this inequality? Again, it's not a number. I can't plug it in. It doesn't mean anything to say negative infinity is less than 3. What is negative infinity? You can't tell me a value for that. All right. So it's not a solution, meaning I'm going to put a parenthesis on it, parenthesis, to indicate that that first of all, this says there is no left endpoint. So how could the left endpoint be a solution if there is no left endpoint, right? So a parenthesis on that. Now we did determine that 3, the right endpoint, is a solution, right? It's the equal to 3 part. So again, a rectangular bracket on that. Okay, and there's the interval notation. This is all the numbers less than 3, from the far left up to 3 are solutions, and including 3 are solutions to this inequality, right? All right, and I guess one other thing too, if negative infinity points out that there's no left endpoint, positive infinity, right, or just infinity, would be used on the right endpoint. If you had solutions going to the right forever, you would use this symbol, just the positive infinity, to indicate there is no right endpoint. There is no largest solution. Okay, and again, always parentheses on those infinities or negative infinities if they're replacing the left endpoint or right endpoint with the fact that there's no left or right endpoint. Okay. All right. So one other example. All right. And then we'll get into some ones where we look at the other way around, where we have an interval and have to write inequalities. All right. So here's another compound inequality. All right. This is remember, this is technically the same as 1/2 is less than x, and at the same time x is less than 7/2, right? You have the two inequality symbols, two inequalities put together, a compound inequality, and both of them have to be true, right? So we've seen something like this earlier, right? This means that every solution, every number that x is replaced with to make this true is between 1/2 and 7/2, or 3.5, right? All right, so I'll do the graph first. Here's the number line. And so here's 0, and then a half would be to the right of that. That's positive half, and then 7 halves is even larger. I'm going to kind of spread these out. This isn't perfect, all right, but I know that 7 halves would be to the right of 1 half because it's larger. And as I mentioned, all the numbers that satisfy both of these are the ones that are greater than a half and less than 7 halves at the same time. That would just be the numbers in between. All right, so all these numbers here in between 1 half and 7 halves. And then we check the endpoints. Now there is a left endpoint, that's the half, where it stops on the left, and there is a right endpoint, the 7 halves, where it stops on the right. And are they solutions? Well, is 1 half a solution? Is 1 half less than a half? No, 1 half's equal to a half. So right away I'm seeing that 1 half does not satisfy. So I put an open point or just a parenthesis on that, whatever you prefer. I like the open point. That indicates to me that this left endpoint, this half, is not a solution. And you may have noticed by now too that if there are just less than or just greater than symbols, you're going to have your open points or parentheses. The endpoints won't be a solution. Whereas if you have the, in the last example, see less than or equal to, you had close points, less than or equal to, greater than or equal to, you had a close point or a bracket on your graph. The endpoints were solutions. So over here I'm seeing another just is less than. So 7 halves isn't a solution, right? 7 halves, yeah, it's greater than a half, sure, but 7 halves is not less than 7 halves. It's equal to 7 halves. So the whole thing's not satisfied. Another open point, or again you can put a parenthesis here, parenthesis here. All right, great. So here's a picture of all the solutions, all the numbers that make that a true statement, the numbers between 1 half and 3 1/2, between 1 half and 7 halves, and then my interval. Again, when you're writing an interval, you always go from low numbers to high numbers, and in this case that would be from left to right. First I write down my left endpoint, which here we actually have one, so no need for infinities or anything here. That's a half. Comma, and then I have solutions from a half up until 7 halves, right? That's the right endpoint. So 1 half comma 7 halves implies that all the numbers between these two are solutions. And then on the ends, is 1 half a solution? No, we determined that it wasn't. So I put parenthesis on that. And is 7 halves a solution? No, we determined it wasn't. So again, a parenthesis on that. So here, this is the interval describing the solutions to this inequality. And again, all three of these things, the inequality, the graph, and the interval, represent the same numbers. And again, and now another little side note. If ever you see intervals like this, where both sides, both endpoints have parentheses on them, and these two are actually real numbers, so not infinity or negative infinity, like I have here, 1 half and 7 halves are actually real numbers. An interval that looks like this is called an open interval. Alright, so when there were both brackets, it was closed, and when they're both parentheses, it's open. And again, as long as you have real numbers as your endpoints, not infinities or negative infinities. Okay, wonderful. Alright, now the last batch of examples I have for you is just kind of going the other way around, where I have to look at an interval and make a graph and write an inequality. Right here I had an inequality and I had to do a graph and an interval. Here I'm going to, in this last batch of examples, you'll see I am taking an interval. Alright, so here's an interval. Write the interval as an inequality and also graph that inequality. Draw a picture of the interval, right? Picture of the solutions. Okay, so remember what this means here. Right, when I'm seeing this as an interval, when I see 0, 5, that means my solutions to whatever inequality I'm about to write are all the numbers between 0 and 5 not including 0, right? So everything between 0 and 5, but not including 0, because you got a parenthesis, right? Not including 0 and including 5. 5 is a solution. 0 is not, parenthesis, 5 is a solution. You got the bracket. Not including 0, but including 5. Alright, so if I were to graph this, right, let me make the graph first. Alright. So if I were to graph this, here's a real number line. Say 0 there, and 5 is mentioned. 5 would be to the right of 0. If I just draw a picture of what I described, this is all the numbers between 0 and 5. Not including 0, so open point there or parenthesis there, and including 5. You can put the bracket or the close point, and there's a graph of this interval, right? The numbers that this interval is describing. And this looks exactly like my some of my previous examples where I had a compound inequality where the value of the variable was between two numbers, right? So when I write this as an inequality, it looks like I'm going to be writing a compound inequality. See where the value, you see my value of x can be any one of these, right? It looks like it's a number greater than 0, but at the same time less than 5, right? So like this, a number that's between 0 and 5. It's bigger than 0 and at the same time less than 5, so between them. Not including 0, so just strictly greater than 0, so no need for the equals to there. But including 5, meaning x is not only less than 5, but x equals 5 also works, right? And then here's the inequality that would have this picture as a graph, the solutions, and also this interval. Right? Great. So hopefully that was pretty simple. Just got a few more here. Pretty simple ones I feel. So again, here's another interval. All right, now be careful. Some people see the thing with the parentheses. They think that, oh, this might be an ordered pair, and plot a point on the coordinate plane. It all depends on the context of the problem. If I'm in this section here where we're given intervals, so I must look at this and know that this is an interval on the real number line, not a point on the xy plane. All right, so just pay attention to context. Read the type of problem you're looking at. Alright, so again, I think it would be easy to do the graph first. So here's the real number line. Here's 0, and then the only other number mentioned here is -6, which would be to the left of 0, right? Less than 0. And remember what an interval is telling us. This interval describes the numbers. I'm seeing -6, 0. That implies that I'm looking at every number between -6 and 0. So all these numbers here between -6 and 0 are good, belong to this interval. But there are parentheses on both endpoints, meaning neither of the endpoints are solutions to whatever inequality I'm about to write. So open point on both of them, or parentheses on both of them. Okay, so there's a picture of that interval, a drawing on the number line of those numbers. And then I can hopefully very easily now write an inequality that goes along with them. And again, we have this betweenness, right? The value that x can be, right? I'll use x again. You can use whatever variable you want. It's just been x throughout the video, so I'll keep it x. So the value my variable can be, notice it has to be greater than -6, but also at the same time less than 0. So it's that betweenness again, right? It has to be greater than -6, but at the same time less than 0. All right. And it doesn't include either of the endpoints, right? So no equal, right? Just strictly less than there. So -6 is less than whatever x is, and at the same time x is less than 0. X is between -6 and 0. So here's an inequality that describes the same numbers as that picture, which describe the same numbers as this interval. All right. All three are interchangeable. All right. So here's an example where the infinity shows up in my interval. All right. So this here, I'm seeing 5, infinity. Remember, infinity on the right side there means that there's no right endpoint. So the solutions will start at 5 and go to the right forever. So this is just simply all the numbers greater than 5, right? 5 and above. And not including 5, right? Parentheses on the 5. Just the number is strictly greater than 5. And I never mention anything about infinity, right? I'm not going to say not including infinity because infinity is not a number, right? The only one that's an actual real number here is the 5. So that's the only one I talk about at the end there, not including 5. Infinity should always have parentheses around it. It's not a number, it's just an idea. Now for the graph, right? Again, I think the graphs are pretty easy to make first. So here's the real number line. There's 0. The number 5 is mentioned. 5 would be to the right of 0. And as I said, this interval 5 comma infinity implies that it's just the numbers greater than 5 are being described there, and no right endpoint. Right. So I'm gonna put a little arrow here indicating that this goes this way forever to a million, a billion, a trillion, a googolplex. A googolplex plus 1, just to the right forever. And 5, the left endpoint, that we actually do have an endpoint. 5 is not a solution, not included. So again, an open point or a parenthesis there. And great. And then the inequality I can write. Now the last two examples, there were two numbers involved. So I had there were two numbers involved, so I had two inequalities, a compound inequality involving betweenness. Here there's only one real number mentioned, and one set of numbers here. There's only one endpoint. So I'm only going to have a single, simple inequality, one inequality. And hopefully you're seeing that all these numbers x are greater than 5. Right? All the numbers greater than 5 are these numbers here. 6 is greater than 5, 7, 8, a million, right? All those numbers mentioned in this picture, in this interval, satisfy this inequality I just wrote. And just greater than, not greater than or equal to, right? Because again, we mentioned 5 is not a solution. 5 is not included. And if we put the equal to in here, or greater than or equal to, 5 would be a solution, 5 would be included. And that'd be it, right? Because there's just one real number mentioned, just one simple inequality. The previous examples, there were two real numbers involved, so we had two inequalities, a compound inequality involved as well. Alright, I have one last example for you. Here we go. Another interval involving an infinity or a negative infinity. Okay, this one has the negative infinity here, meaning that there's no left endpoint. Alright, so there's no left endpoint, but having the negative infinity comma 8/3 or 2 2/3 means that every number from the far left, from negative infinity, every number up until 8/3 is a solution. So this is all the numbers left of 8/3 or less than 8/3, and notice the bracket, we're also including 8/3, including this right endpoint. Alright, so again, the graph. Here's the real number line. Say zeros here. Only one real number mentioned here, right? Again, negative infinity is not a real number, so I'm going to be writing like just a simple inequality with one inequality symbol in a minute. 8/3 is positive, so it'd be to the right of 0. There's 2 2/3. And as I said, this implies there's no left end, and we're doing all the numbers up until 8/3. So to indicate that there's no left end, write a little arrow pointing to the left, going to the left forever, no left end, going to negative infinity. Up until 8/3 at the right end, and it is included. You got the square bracket here, so a closed point or a bracket, a rectangular bracket there. There's a picture of the numbers that this interval is describing. And then finally I can also make an inequality describing the same numbers that this picture is, or that this interval is. Now you're seeing that all these numbers, which again I'll call x, x could be any of these numbers which are all less than 8/3. All these numbers are less than 8/3. So x is less than 8/3, But we saw too that 8/3, the right endpoint, is included. So I got the or equal to added here. So the value I can replace x with is a number less than 8/3 or equal to 8/3, because that's included. That is a solution as well. All right. And there we go. All right. I hope those are all pretty simple. Especially after you do several examples, I think you can get the hang of it. Just make sure you remember what means what. The bracket meant the endpoints included. It is a solution. The parentheses meant that the endpoint isn't included and is not a solution. And the left endpoint comma right endpoint meant that all the numbers in between those were also solutions. Okay. Great. And as always at the end of these, I like to say, try your best to get the material, understand the material on your own first before you go out looking for help. I find that people tend to remember things better. It tends to stick with them more if they've put in the time and the effort to try to to learn things on their own. They feel more proud of it, more proud of themselves. Remember it well. So read through the material. Right? Of course, read your book, read through the material. Read through the author's examples, perhaps even try to work out the solutions to an example before you read what the author did. See if you can learn from any mistakes there. Of course, work out exercises, practice problems in the back of a section. Look for ones that have solutions you can look up so you can check yourself. And don't give up after the first try, right? If after several attempts at a problem it's still not sticking, it's still not clicking, walk away from it for a second. Go back and read the material again, maybe even a third time, because there might be something you missed, or something that when you read upon a second or third reading that'll click that didn't click the first time. But if after several read-throughs of the material and several practice attempts at problems you're still not getting it, then it is not a sign of weakness whatsoever to go looking for help, go asking for help. That is what other people are there for. Ask a teacher, a tutor, a friend, someone in the class who you knows the material well and is willing to help. Look for supplemental materials online. Look for videos on the material, maybe such as this one, or plenty of other ones out there that are better than mine. I assure you can find them, and just keep at it. Right? Be persistent, keep practicing, and also try to go into it with a positive mindset. If you go into something thinking I'm going to hate this, or I've always hated math, well, you're probably going to continue to hate it if you keep thinking that. So you'd be amazed at what changes can happen and how much learning can improve if by just changing your mindset. Trying to go in with an open mind, a positive attitude, and see the difference that could make. So keep practicing, stay persistent, don't give up, and I know you can get it, and just try to have fun with it too. All right, and thank you for watching.